Welcome back. It seems like it's been forever. Like this should be January already, but no, we're not done yet. This close, right? So we have just 2 weeks of classes. I have now posted everything that we are going to go over the rest of the semester, so we're in the home stretch here. Today, a crash course in Longitudinal. That excites some of you. I decided that in the interest of time, I'm not going to make your last assignment over 3-level models because I want you to be able to start as soon as possible. So your last assignment is going to be a longitudinal assignment using generalized models. So those of you who took longitudinal, it will not be anything you've done before. It's going to be a different one. So after today, you will hopefully have everything that you need to do that. As you will see, there's not a lot that's different. It's just a different level of interpretation in terms of what between and within mean, as well as additional considerations as to what the effects of time should look like. But I won't give you anything that's too complicated since we haven't spent a lot of time on it. So we have a quiz due next week. So I'll put that up after Thursday. I hope to have your last assignment up either tomorrow or before class on Thursday. That way you have a full week to work on it. And in theory, you should be able to finish everything during the last week of classes and walk out of here free. Won't that be, yeah, that would be wonderful, right? So did you guys get an email about course evaluations being open? Okay, you should have. So I want to make a deal with you. No, wait for it. So at every other university that I've worked, course evaluations were done on Scantron bubble sheets and handwritten stuff still, which is functionally useless because they ask questions like, were tests fair? It's like, I didn't give tests. I don't know how to answer that question. And so I always did a separate course evaluation via Qualtrics where I could add custom questions that were more useful. And I had always given an extra credit point for people who participated in that evaluation because I hacked Qualtrics to be able to tell me which emails had completed the survey, but they didn't tie the responses, so it was still anonymous. So I got an email from the university system here saying, you can add your own questions to the course evaluations. And I said, cool, I don't have to have a separate survey. And then I realized it wasn't going to let me see who completed the evaluations. Several of you apparently have run into this problem before. So I want to make a deal with you. Okay, here's my deal. Let me find my roster here. So there are 13 people officially enrolled in this class. And I believe, Juliana, they're counting you too since you're enrolled as an auditor. If at least 12 of you complete an evaluation, I'm leaving room for one screw off, right? Like just, if at least 12 of you submit an evaluation, all of you get a point extra credit. You can take that deal? Okay, and so to ensure that that happens, as recommended by the email, it said, give them time in class to be able to do this. So I will give you time the last day of class to sit here and complete the evaluations for your extra credit. I want to encourage you to be as honest and specific as you possibly can, because I really do want your feedback to make things better. So there's no dumb comments. There's nothing that you should feel bad about saying. If there's something that you didn't like, if there's ideas that you have for how things could have been more effective, I am honestly all ears. And so I'll ask the specific questions that I added are the ones that I'm more interested in. Of course, the people who pay me want me to have good numbers. You know, they want you all to like me because that means I'm a good teacher, right? Or something like that. So, question?
Yeah, I wonder if you can send them just a follow-up email to everybody says that, so like 8 out of 13 has finished it.
Yes.
Yeah, so I just want to know if
a little level of accountability.
And then how many didn't do that?
Well, I will do that because evaluations are open. I have to look at when they close. I want to say it's like the 14th or something. They've closed on the 14th. So if you're not here to do it in class, they'd have to complete it by the weekend. But yeah, I can check after class on the last day to see how many people still need to do it.
Yeah, at least we know we did, and then we're not a person that's...
Yeah, so then you can bug each other to be like, hey, did you do this yet? Because I don't think I'm allowed to do that. But I'm going for high completion rates here, so... And I do want everyone's feedback, so we're going to see how this works. If it falls apart, then I may have to go back to Qualtrics, but we're going to try it this way. So, Your last homework, by the way, will be the same because it's generalized models. You can either do 6, which will be SAS, or 7, which will be Stata. That way I can make sure that any discrepancies in the answers are not caused by software differences. So. All right. So do you have any questions on the last homework that you completed before break? I have an example pulled up here. Would it be helpful to go over it at all, or do you feel like that was reasonably okay? Or specific parts that you struggled with?
In section 1,
Mm-hmm.
I don't understand the estimate statement part.
The estimate statement part.
In section 1,
Oh, in describing which terms the estimate statements was used for? Okay, so yes, I can clarify that. So the goal of this was to give you some means of review as to what your model specification gives you in terms of fixed effects at level 2 when you have level 1 predictors. So I had instructed you to do 2 different kinds of centering. So we have the number of published papers, which is a continuous variable, and also the amount of quantitative training, which was binary. So it was either minimum or advanced. And so I had asked you to use group mean centering on the number of published papers. So you would find the mean for each department first, and then take the number of papers for each student minus the department's mean. That's your level 1 predictor. The mean for the department then I asked you to center at, let's see, 3. Here's the instructions for the level 2 predictor. So if you use group mean centering, and you include that group's mean in the level 2 model, what does the level 1 fixed effect become? You got 4 choices: between, within, smushed, or contextual. Do you want me to get out Excel to do this again? Why not? You know what? I've actually saved it from before. I called it the smush chart. Yeah, this one. So number of papers is under this setup. And I had asked you to estimate a model where they were both included. So the level 1 predictor takes on the level 1 within effect, which should explain residual variance, except it can't in this case because it was a logit. The level 2 predictor, which is the group mean minus a constant, becomes the between effect, which should explain the level 2 random intercept variance. And that means the one that is implied by the model but not directly given is the difference between these two, which is contextual. So if you wanted to know the contextual effect, you'd have to write an estimate statement, in this case, for between minus within. That's the difference. For the other predictor, which was whether or not you have advanced quantitative training, I asked you to leave the level 1 predictor uncentered, put that there, since it's already 0, 1, and add the proportion of students with advanced quantitative training, so the proportion of people who had a 1 as the level 2 predictor. When both predictors are in the model, over here, the level 1 effect becomes the within effect, the same as in the other specification. The level 2 effect is the contextual effect. So it's the extra effect of being in a department where a lot of people have quantitative training. That means for an estimate statement, you would have to add these together to get the between effect. Okay, does that help? Good, okay. So the smushed effect is the bad one. That's the one that happens when you put in a level 1 predictor all by itself that still has level 2 variability in it. Then that fixed effect has to do the work of both the level 1 within and level 2 between, which assumes they are the same number. So another way of thinking about this is that the contextual effect is the test of whether or not smushing is acceptable. It is the difference of the between and within. In theory, if the contextual effect is non-significant, that means between and within are basically the same effect. You could use one coefficient to represent both, but that's still very dangerous to do because that equivalence could fall apart if you add other predictors in the model, interaction terms, and so on. So for that reason, I always recommend unsmushing predictors either by doing within between as sort of preferred method, or within and contextual in situations in which the level 1 predictor is categorical, you want contextual effects, or your level 2 variable is not the aggregate of level 1, such as if it comes from a different database or something like that. Okay. Other questions? Yes.
I didn't understand why the answer for question 75 is random variance in the within department number of papers effect, not the random variance in
So the beginning of the questions here, we examined the extent to which the effect, missing an of student level number of papers on employment varied randomly over departments. So it's the random slope that is the focus of this inquiry. First, a random variance in the within department number of papers effect. So that is another way of saying that. So it's a between department variance in the effect of within department numbers of papers. So does having more papers than the others around you matter more in some departments than others? That's a third way of saying it. So we already tested random intercept in section 1. This is random slope. And it's a random slope across level 2 units of a level 1 predictor. That's what makes it tricky. Sure. And because it's a slope variance across departments, you need between department predictors to capture it. Other questions? No? Okay, everyone's looking down. Does that mean you're going over your homeworks and seeing if there's anything you wanted to ask about? Or you're just avoiding eye contact? Because either is plausible, right? Okay. All right. Well, if you think of anything, please let me know. I'm happy to answer questions like, why is this wrong? And sometimes it's because it's not wrong and because I screwed it up. So please let me know if there's anything you think should be correct but isn't. Sure.
Two ratios, which is exactly the same. So I think it's a Q 70.
Q70.
Yeah. So why did you say it's insignificant? Because this ratio is the ratio I calculated from. So that 131, the last one, is by the previous two. And then I think if the other two are significant, this one should also be significant. I'm so confused. And also this ratio you used it twice. One is the question 71 and 17, and the other is the 71 and 73. So I don't know why all of a sudden it became not significant. So I'm so confused.
Okay, let me see if I can unpack this here. So we're talking about the effect of papers, or we're talking about the effect of training?
I think the paper.
Papers, okay. So these odds ratios right here.
Yeah.
Okay.
The last one is just to use the between divided or the within divided by between. So to get the last one. So why the other two are significant and then the ratio became not significant? Why did you get that conclusion?
That's not how I got those numbers. So these, let me go back up here. I think I didn't ask for the coefficients anymore, but yeah. So student level, within level, that is the odds ratio that goes with the within effect. So it's e to the logit for that coefficient. Between is, in this case, it's the coefficient that is directly provided by the level 2 coefficient, the odds ratio for that, so it's e to that slope. And this one is the one that you have to get via an estimate statement as the contextual effect. So it's between minus within. If you take the odds, EXP to that value from the estimate statement, that's where this came from.
My question is why it became non-significant? Because the other two are significant. why this contextual became non-significant?
The contextual effect represents how much bigger the between effect is than the within effect. So it's possible that that difference differs after you control for quantitative training than before. So it's two different versions of the level 2 effect. The between is not considering what individual you're talking about. It's the effect of being from a department that publishes a lot, in this case. The contextual effect, number 32, is the effect of being from a department after controlling for how much you publish.
My question is, how can you judge if it is significant or non-significant? This is the only error I made. It's non-significant. The last one.
It goes with the coefficient in the logit metric. So you would need to write an estimate statement to get the difference between the logit version of the between effect and the logit version of the within, and then take the exp to that quantity.
Oh, to get that percentage.
It's not a percentage. It's a what's anti-log? Is that the right word? E to the is like when you unlog it. So in logit terms, it's log of the odds. You take the log off by exping it, then you're left with odds. So these three are effect sizes. They're not coefficients per se. They're in an effect size metric, not in the logit metric that the significance test directly applies to. But they should correspond. Does that help? Maybe? Okay. Other questions? All right, then how about longitudinal? Yay! A crash course. Because it's kind of funny. There's a lot of this that you already know and quite a bit that you don't, actually, because time is a whole thing in and of itself. It's a level 1 predictor, but it's a really complicated one. And so in the longitudinal course that I taught last spring, we spent like 8 weeks talking about time, because you have to get time right before you can talk about the effects of anything else. And so that's what I wanted to go over today is what are the differences and how you think about multi-level models if your first level is time within person as opposed to person within group. So after this, we're going to talk about different kinds of 3-level models, such as time within person within group. And so all of this will apply. Even if the people are not independent, you'll have to add a 3rd level or otherwise rearrange your levels for other kinds of designs. But time as a level is a unique, special thing that you have to worry about. So this is lecture 7, a crash course. All right. So an overview of things to worry about with respect to time. So this is the series of steps that I want to go through and then think about what are the options within each of these. So the first step here is one you're already familiar with, an empty model. The goal of the empty model, get an interclass correlation, figure out how much of your variation is between versus within, but now it's between persons versus within persons as a different type of sampling design. Then the rest of this is all stuff that we didn't talk about. So you know it in a general way as fixed and random effects of level 1 predictors, but time has additional complications. So we'll talk about those. So step 1, empty means random intercept model. We end up with an intraclass correlation. So the intraclass correlation more generally in a 2-level design is level 2 random intercept variance divided by level 2 random intercept plus level 1 residual. So it's always between over total in a 2-level design. Now what that means depends on what your levels are. So in clustered data where we've been, it was between and within groups. So the ICC was the proportion of total variance that was between groups. It was also the average correlation of people from the same group. Now if we put our longitudinal hats on, if we have time within persons, the ICC is the proportion of variance that is between persons in the intercept. In other words, it's the proportion of longitudinal variation that is actually cross-sectional. So if you think about mean differences between persons, that's what you would have gotten had you started out with just one occasion and a whole bunch of people, right? If you add another occasion, you still have to indicate how much of that variation was just from adding different people and not another occasion. So the ICC gives you the proportion of variance that basically would have been there anyway had you just measured them once. It's a better estimate because it's the mean across occasions, but it's still cross-sectional variation. So the other way of thinking about it is the correlation between occasions from the same person. So how related are a person's set of occasions over time? If the ICC is close to 0, what does that mean in this context? So not very much between, which means a lot within, meaning people don't really differ from each other that much, but they do change a lot over time. They change or they vary. If I had an ICC close to 1, all between, meaning you just wasted your time. Did I tell you that story? I'll tell it. I don't think you guys have heard the story. Some of you may have. My second time teaching this course, Longitudinal, at Penn State when I was a postdoc. Back then I had them all do projects using their own data, and my first assignment was estimate an empty model, calculate an ICC, make me a spaghetti plot, so a plot of predicted trajectories. And one of my students gave me an assignment where the ICC was literally like 0.99999999999. And he was doing this as his dissertation. And he was going to be the first person in his field to tackle this research question in a longitudinal study. And so I asked for a meeting with him, and I had to say, dude, no, you're not, because you don't have longitudinal data. An ICC of 1 means they gave you the same answer every single time you asked. People just started out and they just kept going right where they are. So you didn't need to ask them the same question 5 times. All of your variation is cross-sectional. And I don't know what happened to that dissertation because he dropped my class and I never heard from him again. And I felt bad about that for a minute, but then I thought, you know what? I told him this in late January, not in April when he was trying to defend. And someone said, why didn't you find anything significant? Well, because you got to have variance before you can find anything that predicts it, right? It's really hard to predict a constant. Impossible, dare I say. So yeah, this is like step 1. Do you even have longitudinal data? Anything under 1, play ball. If you got 1, it's a level 2 predictor. So if you're ever handed a strange data set and you're not sure, honestly, at what level a variable is measured, do this. If you end up with like no residual variance and it's all random intercept, you can be pretty sure that it's just a level 2 predictor, or functionally is. There might be 1 or 2 little dots that are not the same, but it functionally is. So you would do this for any level 1 outcome and any level 1 predictor. This guides you to what kind of predictors are going to be more useful. So if I told you that I had an ICC of 0.8, do I need person level things or time level things as my predictors? My ICC is 0.8. Do I need person level things or time level things to predict my outcome? Person. That means most of the action is at level 2. If I had an ICC of 0.2, it'd be the opposite. That means most of the variation is over time. I need predictors that vary over time to be able to capture that variation in the outcome. So it's diagnostic into your model building process.
Can you say that again?
Sure. So if you have an ICC of 0.2, that means most of your variation is within persons, is longitudinal, and so you need predictors that are time specific, that change over time, so that you can predict the variation over time that goes with it. Sure. 0.6. It's roughly half and half. That means that you've got a good shot at either half, depending on what you're looking at. There's no situation in which you wouldn't run a longitudinal model accounting for both halves unless it was literally like ICC of 1. In that case, it's functionally cross-sectional. So it's just something to report as a descriptive statistic because it's not going to be right. I mean, the ICC assumes that you have constant variance and covariance over time, which is almost never the case. So this is just a jumping off point. Now, what should time be? I've actually written quite a bit about this, as this is something that I was drilled into me as a postdoc, that it's not obvious necessarily what time should be as a predictor, and it depends on the context of your study. So the situations in which you have to worry about this are what's known as accelerated longitudinal designs, or sequential cohort designs, or overlapping cohort designs. That's where, like, if you take, say, first, second, third graders, and you measure them each for 4 years, something like that. So the third graders go 3, 4, 5, 6, the second graders go 2, 3, 4, 5, and the first graders go 1, 2, 3, 4. So in theory, you've measured from first grade all the way to 6th grade, even though not a single person was measured that long. So that's a way to sort of cheat into a longer longitudinal study than you're actually doing. In those kinds of designs, you have to be very careful not to assume that one common trajectory fits all of those different people. It's the same exact problem as smushing. To the extent that people differ in time at the beginning of the study, so they come in at different ages, they come in at different grades. If you're studying some sort of like a disease progression, if they come in at different times since diagnosis, that cross-sectional variation probably has a different effect between persons than the effect of changes from that point in time within persons. So in the longitudinal context, the idea that the between differs from within is more the cross-sectional age trend differs from the longitudinal age change. In a school context, it would be like, let's say that the school implemented some new program halfway through your study. So this year's third graders don't look like last year's third graders. That would be enough to cause a disruption in how the cross-sectional and longitudinal effects of grade operate. So all the stuff that I said about smushing applies to time as well, in situations in which people differ in time at the beginning of the study. So I can give you some readings on that if you're interested, but just to know that this isn't always an obvious question. If you're in the situation where everybody starts at the exact same time and everybody's followed for the same length of time, then all of these decisions are moot, but most of the time it's not the case. So, centering point. So we want to center time so that somewhere in the data is time 0. This is a choice of convenience. There's no right or wrong answers. I will say that if you forget to center time, you could run into estimation problems. So one time I was helping somebody troubleshoot a fairly complex model using older adults. And they had entered in age as a latent variable for something and sort of forgotten about this idea of centering. So if I'm dealing with, say, adults from 80 to 100, and I forget to center age, to what kind of person does my intercept apply? Someone who's 0, a newborn. Do you think that it's going to be easy to estimate a mean for a newborn using data from old people? If it's just a regression line, that's fine, right? Because you'll just be like, all the way down, right? The model can handle it. But what happens if I try to add a random slope for age? Then what does my random intercept variance become? Conditional on age equals 0, which means not only am I estimating a predicted mean for newborns, I'm estimating the variability across newborns using data from old people. And I've seen the model literally not converged when you tried to do that. So you want to keep a time 0 somewhere within the span of the data so it doesn't have to extrapolate too far. In terms of what type of effective time you want, this is something that probably should be applied to quantitative predictors more broadly, but for whatever reason isn't. But when it comes to plotting time, it's important. So if your time is balanced or unbalanced is the big distinction here. So balanced to me means that everybody is on the same schedule. Not necessarily equal interval, but on the same schedule. So if I brought everybody in at time 0, I had them all come back 3 months later, and I had them all come back a year later. That's balanced. It's not equal interval, but everybody's on the same schedule. If I measured everybody at time 0, and I asked them to come back 3 months later, but some people had to reschedule and they got sick and they had to reschedule again, and it was more like 4 months later or 5 months later, like it's messy, right? That's unbalanced. And so whether or not you have balanced or unbalanced time dictates what kinds of models you can fit. There's a lot more options for balanced. Unbalanced isn't a deal breaker. And that's actually one of the hallmarks of when longitudinal models, multi-level models, become most useful, is in handling unbalanced time. It allows you to treat time as a continuous predictor and fit a trajectory through whatever points you happen to have, even if they're not all in common. So the first step in the longitudinal class to figuring out what kind of trajectory you need is to plot means. So there is a model that goes by a special name in this genre that you're already familiar with. How many of you have heard of repeated measures Anova? Come on, I know you've at least heard of it, even if you've never done one, right? That treats time as categorical. It estimates a mean, basically for every occasion, treating it as balanced. That's what you do first. It's called saturated means, in that it takes as many fixed effects as you have means, but it perfectly recreates each mean. You make a picture. Is the line straight or is it bendy? Does it look continuous or is it kind of discontinuous? And that picture guides you to what family of trajectories is going to be most useful. If time is not balanced, if people are off a little bit, you need to round them into convenient intervals to be able to make the same picture. You would never round time in analyses, though. Question?
They are using the food pantry in different times whenever they need it, and
Mm-hmm.
they get amount of food from there. So it's a longitudinal data set, but I have never looked at it in a way because I don't have this ability yet. So but this means that this data set is not balanced.
It's not balanced. Yeah, unless so do they go to the pantry like every week, or could they go like any day of the week?
Yeah, some of them just have visited only once, some just come back. So it depends on their need because it's just for a limited amount of time. It's not something like they use it all the time. Some people who feel like they need it, they go there whenever they want, some just once or twice.
That would be an unbalanced design. Yep, that's a good example. Yep. A lot of times people try for balance, but people don't always cooperate, right? They don't come back when they're supposed to. So it becomes unbalanced because people are late or they're early, and this is real life. The same thing can happen in school settings, though, right? We're in the College of Education. There's a lot of testing that happens like in the fall and in the spring, right? So if you test someone in August and you test someone in May, you get a different pattern of change than if you test them in November and February, even though they're both fall and spring. So you want to pay attention to exactly how much time has passed. You want dates in your data set that you can compute distances and let the computer do it, by the way, because every program has date functions that understand how many days are in a month, which years have leap years and shit like that. Like they know all that. So you don't have to do it by hand. So these models, the hallmark of them is that they're able to accommodate data as it is. Time is just treated as a level 1 predictor. It doesn't have to be in nice, convenient intervals. It doesn't have to be the same for everybody. It is what it is, and it doesn't have to be complete. That's the other part. Yeah. There we are.
Did you say that time, okay, you don't necessarily have the same interval, but everyone's on the same schedule? Isn't that what you said?
That's balanced.
Yeah, correct. But what do you mean, because I thought in this situation that you just gave, you're saying that the intervals aren't the same. I guess to me they mean the same thing in my head. Can Can you elaborate on what they mean?
Sure. So if I had time 0, 1 month later, 2 month later, 3 month later, and everybody followed that schedule exactly, then that is both balanced and equal interval. So the distances in time are equidistant, and everybody's distances are equidistant.
But it doesn't matter if it's like at the same time. Is that what that means here? So it could be like someone, like the example you gave with the test scores about how it was spring and the other one was fall, but
Mhm.
they're not necessarily the same.
Yeah, I would call that unbalanced. Like you might aim for balance. Same distance in time is irrelevant to that. Like they have to be balanced in order for there to all be the same. If they're all each on their own schedule, then the distances are likely to be not equidistant either. So if you had everybody come at time 0, time 3, and 1 month or 12 months later or something like that is not equidistant, but it's balanced because everybody's on the same schedule. Like in her food pantry, if everybody could only show up on Saturdays, that's balanced and equidistant. If you could only show up on Friday or Saturday, right, then you're starting to introduce unbalance because one family had to go 6 days without food and the other made it to 7.
Isn't it the same interval though?
It could be, but not necessarily. So if 1 week that you came on Friday and the next week you waited until Saturday and then the next week you came back on Friday, your intervals are not equal.
So is that still balanced?
No.
Okay. I thought you just said though it's not the same interval. It doesn't have to be.
So like the tightest case is balanced and equal interval. And then there's balanced, not equal interval, and then just unbalanced.
Okay.
Sorry if I'm making it worse, but that's do you have a data set in mind that you're thinking of, or just trying to understand the words? Okay. Okay, Amira? Mm-hmm.
In one of the projects we are working, there are 5 cohorts, but all of them are taking their pre-test in the same day, but every one, cohort 1 started earlier, the next cohort the next year, and it goes like that, but their pre-test is in a specific time, and the post-tests are specific times, but the year for each cohort is different. So if we combine all of the cohorts together, is it balanced?
That is a case of what I would call like an accelerated design. I would want to have cohort as a level 2 predictor because you can't make the assumption that they were all equally the same, and it may be the case that each cohort has a different trajectory. So I think of that more as a predictor rather than as a characteristic. So pretest and posttest. Did everybody take pretest together and everybody took posttest together? No, it was like when they could get it, that's unbalanced. When you're dealing with people, it's usually unbalanced, at least a little bit. Now, whether it's like if it's the next day, and the interval is 6 months, it's like, close enough. But if you're doing like a weekly study and someone does it a day late or 2 days late, like that's more of a big deal. So the models you can do an analysis no matter what. You have more choices when it's balanced. That's what I'll say. Technically just 2, but if you have 2, then repeated measures ANOVA is fine. It's 3 that it takes to do anything that's more interesting, to be able to differentiate individual change from measurement error.
What's the consequence of treating non-balanced as balanced?
If you treat unbalanced as balanced, you are rounding time. You're introducing measurement error for no reason. So just as you wouldn't take any sort of predictor and cut it up into groups, median splits are bad, right? Grouping things, introducing measurement error is generally not a good idea. There are strategies where you can actually test if unbalance matters. I could talk about that if anyone cares, but the second half of chapter 10 of my book has an example doing that. But it's just one of those things where if you're only taught repeated measures ANOVA, you will round things into intervals that are the same for everybody because the model treats time as a categorical predictor. That's all you would know how to do. And so these models don't have that requirement because time doesn't have to be categorical. So yeah, the other part here is that the means that you get from this Anova model are going to differ because you're using some kind of likelihood as opposed to least squares. So this is sort of a common misconception. People think that Anova is bad. There's nothing wrong with Anova. Anova is a very specific type of variance-covariance structure, and if your time is balanced such that you're not creating measurement error, then cool. The problem is least squares. Least squares is the enemy. And if you're using maximum likelihood or residual maximum likelihood, every occasion that is complete goes in the model because the data set is per time per person, a level 1 data set. So if you have somebody who has 7 out of 8 occasions, those 7 go in. If you're using least squares instead, if you have somebody who has 7 out of 8, they are kicked out. So when people say you shouldn't do Anova, they say you shouldn't do least squares. What we know of as Anova models, one is the univariate approach to repeated measures Anova. That's a compound symmetry model, which is equal variances and equal covariances across time. The other one is the multivariate approach, where each occasion gets a different variance and all possible covariances are estimated. Those are fine. But if your data aren't complete, whole people will get kicked out if you use least squares instead of likelihood. So that means that if you run just means on your data set, like descriptively, you will get different answers if you have missing data than if you do this saturated means Anova model. These are the means that you want to report because they are the ones that are being estimated as if the data were complete under the assumption of missing at random, and those are the means that subsequent trajectories are going to be trying to capture, not the observed means, which are missing completely at random. So they're going to be different to the extent that you have missing data, and you'll have to be careful to clarify that when describing them. Okay. Other questions?
How do you create a rounded number? You have to use all the available data with the misses and then to create a rounded variable?
There's a round function in most data sets that allow you to round to whatever integer. I would use that just to make a picture. I would not use that in any kind of analysis. Because otherwise, if you try to estimate this model with unbalanced time, it's going to try and come up with a separate mean for every unique value of time, like down to the 17th decimal, and it may blow up when it tries to do that. Okay, others? Yeah.
I wonder if we have like unbalanced data, like every person got different time trajectories. For some time point, maybe just one person show up. And how would that affect the estimates? Like, do you trust the individual lines, or you are more?
So what this would do is lump everybody together and come up with like a mean across the people that have that occasion. So it'll still give me a mean for somebody who has 1, but the standard error around it will be like this.
Okay.
So you'd want to look at a plot of means and sort of a confidence window around it and not pay too much attention to those that are like this. Others? All right. So kinds of longitudinal data. There are lots and lots of kinds. The one on the left is what most people think of, and these are the types of data that would come from studies of within-person change, where the objective is to see growth or decline and to see how people differ in their rates of growth or decline. So trajectories, if you plotted them for individual people, might look something like this. So models that are designed for these types of data are often called growth curve models, even though they apply equally to trajectories that are linear as to nonlinear and that are declining as to growing. So if I'm doing an analysis of aging where everyone's declining, that is still a growth curve model. That's just what it's called. If you want to sound extra fancy, put the word latent in front of it. It's a latent growth curve model. That's the same damn thing. That means you used SEM software instead, but whatever. The other kind which is like the food pantry example would be one that probably follows this, is what I call within-person fluctuation. And here, time is just a way to get a lot of data per person, but you're not necessarily interested in which specific day it is. So if you're interested, say, in how social support helps someone overcome stress, or how two partners, if their bad mood reflects badly on another partner, and whether their bad mood affects that partner, those kinds of variables that fluctuate, like emotion and stress and food insecurity and stuff, like they just kind of, the objective here is not necessarily to model time, it's to model the processes that are unfolding over time and individual differences in those processes. So these are all equally longitudinal, it's just that different types of data lend themselves to different types of models. So we're starting the overview with the one on the right, types of models that would go with this with respect to time. Most of the time you don't have to worry about a trajectory through the means. Like each of these people is flat, like time doesn't matter per se. A random intercept would allow each person to have a different intercept, and that would be enough. But you still have to deal with the fact that occasions that are closer together are probably more related than occasions that are further apart. And so I just want to overview a couple models that are designed to tackle that kind of data. So this is what I said a minute ago in matrices. So you can think of possible models for within-person fluctuation types of data as on a spectrum from parsimony to complexity. And the ends of this continuum are the models that you know of as variance of repeated measures ANOVA. On the left is a structure that's known as compound symmetry. This is what's given to you by an empty means random intercept model. On the diagonal, you're saying that the variability, so this would be like time 1, 2, 3, 4. The variability at each occasion is part because of between person level 2 intercept differences, that's my random intercept variance, partly due to within person level 1 residual variance. And how much is U versus E is your interclass correlation, right? U over this total is interclass correlation. And so this model form is called compound symmetry. What it means is that each occasion is predicted to have the same amount of variance, and that the covariance between each occasion is the same too. The only way this can be true is if everybody changes the same. That's the only way this can be true. Otherwise, if people are on different trajectories, they spread themselves out, the variability over time has to change as a function of that. So this is like the simplest model that would be plausible for longitudinal data. It can work reasonably well for fluctuation data, but the covariances is the part that might be tricky, because this assumes, let's say that I measure somebody every week for a year. This model says that week 1 is just as correlated with week 2 as week 1 is with week 52. Could be, not so likely. So the covariance part is usually what's problematic. That compound symmetry model works if you have balanced data or unbalanced data, because every occasion has the same variance, and so it doesn't really matter if you have different occasions. Every set of occasions has the same covariance, so it doesn't matter which occasions those are. So this model only has 2 parameters. U0, random intercept variance at level 2, E, level 1 residual variance. On the other side, the most complicated model you could ever fit to longitudinal data that have to be balanced, by the way, is what's known as unstructured. This is the multivariate approach to repeated measures ANOVA, where each occasion gets a separate variance, and all possible covariances are estimated separately. So if I have 4 occasions, an unstructured model for the variance takes 1, 2, 3, 4 variances, 1, 2, 3, 4, 5, 6 covariances. This model has a special name in the SEM literature. This is the saturated H1 model. This is perfect. Everything you're trying to do is trying to get close to this using fewer parameters. Now, why this can only work for balanced data is that every possible occasion gets a separate variance, and every possible combination of occasions gets a separate covariance. So there's no room to fit, like, you know, week 1 1/2 and week 2 1/3 and other like oddball things in here. Everybody has to share the same matrix for this to work. When you fit growth curve models using SEM software, you have to be careful to see if your software forces your occasions to be balanced or not. In M+, for instance, there's an option called T-scores that allows for unbalanced occasions. Does Levon have that? Do you know? No, it doesn't, or you don't know?
I don't know.
You don't know? Okay. So just be aware of this. You can buy your longitudinal model at the SEM store just as much as you can buy it from Proc Mixed or whatever, but not all SEM stores allow you to purchase unbalanced time. A lot of them force you to round it into convenient intervals, which just destroys the whole point. So, by the way, this matrix, only when this matrix is fitable for balanced data is measures of absolute fit possible, because this is the answer key. If you have unbalanced data where each person is characterized by a different matrix, there is no joint answer key that you can estimate. So that's why at no point in this semester have we talked about absolute fit. It's not done for multi-level models. We've talked about relative fit. We've talked about -2 log likelihood going down, which means if you add something, the model gets better, but we don't know if it's like good or just less shitty, right? It's relative. Okay. So if you're in this sort of world here where you're doing fluctuation, basically you have two concerns. Does the variance differ across time, and does the covariance differ across time? There are different patterns that you can put on the data that are more complicated than compound symmetry and less complicated than unstructured that hopefully do as good of a job. Most of these require equal interval data, and most of them require balanced. So let's see here. So these are what's known as alternative covariance structure models. If you take a class on longitudinal data from the stats department, I guarantee you'll talk about these. They're real big in like the agriculture literature and stuff like that. But in order to fit these, we have to review the names of all the matrices. Remember this? G and R and V and Z and all that stuff? This is straight out of the manuals for the mixed models packages. So we have R, which is usually level 1, unless there's no G at level 2, in which R is all the variability. G and R combined equal V. So these models differ in whether or not they do the level 1 versus level 2 split, or whether they just try to pattern everything all at the same time. Here is a table from my book that lists all of the possibilities that I discussed and which ones are nested under which other ones. So there's a whole set of these. I will give you, let's see, the one that I like the best. I skipped a whole lot of this because this is the most boring thing in the world to talk about. It is, it truly is. The one that I like the best is what's known as a random intercept plus an autoregressive R matrix, where you take your random intercept, put it over in G, and then you put an autoregressive pattern on the level 1 residuals. Autoregressive means that occasions that are 1 unit in time apart are correlated R, occasions that are 2 units in time apart are correlated R squared, 3 units in time apart are R cubed, R to the 4th, R to the 5th. So you're estimating only one parameter that allows occasions that are closer together to be more related to each other, but you're controlling for a random intercept first, which is usually the primary source of correlation. So that model you can fit for balanced or unbalanced. It only takes 3 parameters no matter how many occasions you are. So if you're doing fluctuation types of analyses, that's the one that I would probably recommend. All of these others are more complicated but likely less useful because they don't apply to unbalanced data. So for those of you from the spring, this is the whole thing where I had the jeans. Remember that? The jeans. So these are sweatpants. This is skinny jeans. I had a whole thing to go with it. See, because unstructured will always fit, like your sweatpants are always going to fit. No, they will. Like, 'cause they're designed that way. If you outgrow your sweatpants, you have done something wrong. Nowadays, they're called like athleisure, but they're sweatpants still. And skinny jeans is like compound symmetry. It can work for some, but skinny jeans aren't meant for everybody. You will never see me in a pair of skinny jeans, because that's just not going to happen. They're very restrictive. Much like this covariance pattern is very restrictive. All right, so that's that. Now change stuff. So when you're on the left, when you're focused on modeling change, you have to be able to do two things. Number one is describe the average trajectory. So what happens on average? Are people going up or are they going down? Are they going up in a constant way or is growth slowing down over time? What is the function that these means are creating? But then on the other side of the model for the variance, which of those aspects of change show individual differences? So we're talking about fixed and random effects of a level 1 predictor of time. What we've done in this class this semester is exclusively, I think, in terms of level 1, fit linear trends, right? In all of your examples and all of your homework, you had a within-person effect and it was linear. You had a between-person effect and it was linear most of the time. For time, that's rarely plausible, that people keep growing and growing and growing and growing, or declining and declining and declining, particularly in longer-term studies. So more complex functions are often necessary to describe their data. So the two endpoints in terms of modeling change and the model for the means, parsimony to good fit. Parsimony is the empty model. There is no change. That's where you just have an empty model. You say that every occasion gets the same mean. Cool. The most complex model is saturated means. That's only possible in balanced data. That's the Anova model. That's where you estimate as many means as you have, as many parameters as you have means. Something in the middle is what we're typically going for. We're trying to figure out what type of trajectory created that pattern of means. And if we can summarize the trajectory using fewer parameters than all possible, we win. So there's lots of options here, and this is what takes a good 8 weeks or so in my course to go through. Polynomial effects of time, piecewise slopes for different effects of time, and nonlinear slopes for truly nonlinear trajectories. On the variance side, it's the same idea as before. We're still trying to find something that's in between that fits as well as possible but spends fewer parameters, but that's what random slopes of time do. So for instance, if you have a random linear effect of time, that creates a pattern of variation across time that is quadratic. It's at a minimum at some point and it grows on either side of that. If you have a random quadratic effect of time, that creates a pattern of change over time in the variance that's quartic, based on time to the fourth. And the covariances between occasions are time dependent as well. So that's what random effects of time are designed to do, is to model this using fewer parameters and to be able to extend it to unbalanced data by using trajectories that interpolate between occasions rather than estimating every occasion as a separate thing. Okay, so models. Let's start at the beginning. Empty model. Remember this? I call it an empty plus within-person model because once you add more than one occasion, you're able to differentiate between person from within person. If you only have one occasion, you've got between person and that's it. So the same ideas that you've already seen, a different set of subscripts. This semester I've been doing YPG for the generic models for persons within groups. TI is what it is for today, time within individual. Now I'm saying individual because it could be individual person, it could be a department, it could be a school, it could be a rat, it could be whatever you want. No, seriously, I used to have people from that did neurobiology, they got their rats addicted to cocaine and shit. I had them take my longitudinal class. So it could be time within rats, that's a thing. But individual somethings at level 2. So we have all the variation in an outcome split into two kinds. We have U0I, that's my random intercept. Now it's each person gets one, which is why is your mean so different than the grand mean? So these are between person variance in the intercept, differences, that's inter-individual differences at level 2. Within a person, after you give them your own mean, why are you different this time than last time? That's E, which is level 1 residual, which is intra-individual variation and within-person variance. So an empty model in a multi-level model notation system would look like this. So exactly the same as you've seen, different sets of subscripts. So Y for each occasion, for each individual, is a function of an individual specific intercept. Beta 0 is a placeholder. Beta 0 I is not a thing. It goes to level 2, which does hold things. So gamma 0, 0, that's my fixed intercept. So if I have a random intercept with it, this is the mean of the person means. Random intercept is how far off each person's mean is from the grand mean. After each person gets their mean, it goes back into level 1 and picks up E, which is how far off you are this occasion from your own mean. So U0 variance is between persons and the mean over time, is cross-sectional. E variance is fluctuation around your mean, is longitudinal, is level 1. And if you fill them both in, the composite equation looks like that down there. So for longitudinal data, the same as for cluster data, this is always step 1. Figure out how much of your data is actually longitudinal versus cross-sectional. And I would do this for not only your outcomes, but any level 1 predictors as well, which means things that change over time. So next step then, incorporating time. And you've seen this slide before, but it had different words on it. Fixed versus random effects. So on average, is there an effective time? Is the line describing the sample means anything other than flat? If so, we need a fixed effective time. Then second question, the question that is not answerable by Anova, does the average effective time vary across persons? In other words, do people need their own slope for the effective time? And if so, they need a random effect. So assuming we have a random intercept in every figure, here's one option. So if the x-axis is time, the heavy black line is the mean for the sample and each individual line is for a separate person. This picture shows no fixed effective time and no random effective time. No fixed, because on average there is no change, and no random slope, because everybody, no changes the same. That one flat slope is good enough for everyone to share. You can also have a fixed effective time, so in this case we would have a positive slope that describes the line of the means on average, and everybody can share that same positive slope, so we don't need a random effective time. These two top boxes, A and B, are the only situation in which compound symmetry, having only a random intercept, would be appropriate, because the lines are parallel. If you don't have a random effective time, if everybody changes the same, or no changes the same, then all you need is differences in the intercept and you're good to go. This is the most interesting case. So let's say that you didn't ever take these classes, you only had repeated measures ANOVA. You did a longitudinal dissertation. You collected data for a year. You get all the data, finally, you thread it through SPSS, and it comes back, no fixed main effective time. Wah, wah. You're like, am I still gonna graduate? I just wasted a whole year. No, you didn't, because if you came to see me in tears, I would hand you the Kleenex that's sitting on my desk for this very reason. I do a lot of data therapy, as it were. And I would have you make a picture like this. And if I got a picture like this, I'd be like, no, really, this is super cool. Because what happened is that on average, it looks like there's no change. That's because some people grew and some people got worse. Now your study just got a lot more interesting. Don't you want to know why you had these different outcomes? So in this case, we would have a random slope because everybody needs a different slope. The common one does not hold for everybody. The common one might be an artifact of combining different kinds of people. So we have a random slope, but not a fixed slope. So just because if you have a fixed effective time that's not significant, it doesn't mean game over. You can keep going to test a random effect. And the same is true in cluster data. On average, you could have an individual variable that doesn't matter, but it does have a random slope. So that could happen for something like a gender difference. It's possible that in some schools, boys outperform girls on average, and in other schools, girls outperform boys. So that means on average, you might have no gender effect, but you might have a random gender slope across schools because sometimes it favors boys and sometimes it favors girls. Same can be true with respect to time. And you can have both. You can have some sort of average trajectory and individual differences from that average trajectory. These two bottom situations illustrate these two bottom pictures illustrate situations in which a compound symmetry model fitting a traditional univariate repeated measures ANOVA would lead you astray, because those models assume equal variances over time. But if people change differently, the variance has to change over time. And so does the covariance, although that's not able to see in this picture. So that's what random effects of time actually do behind the scenes. Not only are they substantively interesting, but they also allow you to have a pattern of variance and covariance across your occasions that better matches that of the data. So if you see, if you just do descriptives on your data and you see variance that's changing over time in sort of a monotonic kind of pattern, that's a dead giveaway that you have random slopes. That's what they're for. They were developed for that situation. So if we go from empty model, where there's no effect of time whatsoever, and we add a fixed effect first, so we're going from A to B here, it would look like this. So now we have two betas at level 1, an individual intercept and an individual time slope. So now we have two level 2 equations. We're adding only a fixed effect of the time slope so far, so everybody's supposed to get the same time slope according to this model. In doing so, which variance should this new fixed effect of time explain? Level 2 person variance or level 1 time variance? So we're adding a fixed linear effect of time at level 1. It should explain level 2 person variance or level 1 time variance. Yeah, I've heard both votes here. So first question, is there any error term in its equation that goes with it? Not yet. That means it has to come back up here and explain E. So time is a time varying predictor. Which occasion it is, I'll explain some of the residual variance. So if I go back to, let me find this picture right here. The empty model says there's no effective time. It's plotting this. If I go from this to a model that has a slope on average, that will reduce level 1 E variance. The E's will be diminished because you're better fitting a line through them. So level 1 residual variance should be explained by fixed effects of time. There we go. The only other thing that changes when you add a fixed effect of time is that this fixed intercept goes from being the mean of the person means to being the expected intercept specifically at time 0. So it becomes conditional on time. The same way that the intercept has been conditional on the 0 values of predictors the whole time. If I add random time, so this would be picture C or D. I pick up U1. So U1 is a random linear time slope. It is how far off your time slope is from the average time slope. Just like U0 is how far off your intercept is from the average intercept. It's what allows individual differences in change. So if you put them together, each person's individual slope is the fixed part that everybody gets, and the U1 part that is unique to them. Don't think I have, no, I didn't put that picture in. Not shown, but also gets included at this point is a covariance between U0 and U1, because the intercept and random linear time slope from the same person are likely to be related. So I'm going to ask you a trick question before we go. Which variance did I explain by adding U1? Yeah, I like that answer. You just got off the plane from Japan and you pulled that out. That's awesome.
Super jet lag.
Yeah, super jet lag to the rescue. Kind of level 1, but realistically, no, we didn't explain anything. We broke out level 1 variance into this. Now, the reason I resist the explain, I've seen people use that terminology and I just resist it. This is an error term. We don't know why some people grow faster than others. Just like we didn't know why you were off your line today. What we know is that some of the error is systematic to the interaction of a person by time. So it's kind of like a generalizability idea, right? There's a random effect of person by time. That's what this is. So yeah, I would say you didn't explain a variance, you added one. You partitioned what used to be just called within person variance into how much of that is actually between person because of differences in the effect of time. So at this point, your model has 3 different kinds of variance. U0, if time 0 is the beginning, which it often is, it's why do some people start out higher than others? Meh. U1, why do some people change faster than others? Meh. And E, okay, after I gave each person their own intercept and slope, so long as you have at least 3 occasions, it doesn't perfectly explain all the data. So why are you off your line today? You were predicted to be here and you're actually down here. What's up? That's E. So if you think about what kind of predictors logically can explain each of these kinds of variance, why did some people start out higher than others and why do some people change faster than others? Those are between person constructs. We need things that vary between people to explain them. People things that don't change. Why are you off your line today is a within person idea. We need things that change over time. So if I have my own line that's different for me because I have a PhD and you don't yet, and I have an error term that describes why I am killing today but I'm going to do crappy on Thursday, that within week variation can't be because I have a PhD and you don't. It's because I don't know, but I had a PhD today and I'll still have one on Thursday because they don't take those away. Even if you don't have significant findings, they don't take them back. So that can't be. A between person construct cannot explain why you're off your line today. That has to be something that changes daily. Ta-da! See this? It's like you know this already, but not really, right? It's the same, but it's not. And so what makes this tricky, what we'll get to next time, is what happens when you need something other than just a linear effect of time here. You need extra fixed effects and extra random effects. So I want to give you a little bit of a tour of what other kinds of effects of time that there may be. Your homework, though, I think will stick with linear because that's enough of a jump for one unit. Okay? Okay. All right. Thank you, everybody. We will see you on Thursday.